So who's our next presenter? As I said, he's coming from Germany. Markus Harrer is a software engineer who's passionate about improving the way we do software development. He specializes in the analysis of software data, such as source code, application performance data, or version control repositories to show the underlying problems of the symptoms we face on the surface. He's an active contributor in communities on the topics of software analytics, software architecture, software modernization, and worldly maps. When I asked him the question, what is the key takeaway and the golden nugget for the future developers, he said, invest in learning, not only scratch the surface. So please welcome on stage Software Analytics with Data Science on Software Data with Markus Harrer.
Hello, everyone. Hello. Yeah, welcome to my talk, Software Analytics with Data Science on Software Data. So I think the title spoils a little bit what this is about, this talk. We will take a closer look how you can use data science techniques on your software data in the end. So the first question is, why would you do this? Sounds just like a good idea for your newly shiny software system? No, actually not, because it's more or less a thing for this kind of systems. Legacy systems in the end. And yeah, we have a problem here because with the older software systems, there are plenty of batches or patches here and there. And if we want to get rid of such kind of systematic problems that we face in there, so things that don't work as intended, we face a competition between different kinds of stuff when we want to develop and maintain these kinds of software systems. So for example, there are always those features that bring money for the business, of course, and can be easily seen. That's one kind of category. We have bugs that take money away. If something is broken in a software system, we can immediately see this as well, and we lose money. And then there's another category, which is architecture. Architecture is believed nowadays that it brings value. Maybe it's not so easy to see for non-technical people, but we believe in it. And yeah, we have to figure out what a great architecture is. And then we see, yeah, it actually provides value as well, not only for developers, but also for business people. And there's this thing, yeah, that nobody can see in the end, and which sucks out all the money and the value of a software system, which, yeah, is not an easy task to make it visible to management. And in the end, my approach, or what I wanted to do a few years ago, yeah.
Sorry, what it is, because from here we can't see your laptop.
You cannot see it? Yeah, then I just go out of the way here. And maybe you can also switch the seats later on if there is something in between. Thanks a lot. So what I wanted to achieve a few years ago was to find somehow a mechanism where I can communicate these strange things to management very easily. So what to do? So my first contact here with software analysis tools was born. So I thought it would be a great idea to build up an ultimate software quality dashboard where you have some gotchas or even traffic lights where you can see how your project is going, what the real problems are, including some warning signs, for example, with alerting. So if you see, oh, there are these nasty problems in our software system, how can we actually use some tools that are already there to make them visible? Somehow, yeah, this approach failed a little bit because our very specific problems in legacy systems are very unique. So there is no tool to rule them all, no metric that can show how the maintainability of our software system is. But luckily, I found another technique, or a real great discipline, which was called empirical software engineering, where plenty of ideas how we can, yeah, in the end, make those very specific problems more obvious were, yeah, in the end, part of. So I thought, yeah, well, maybe I cannot use this kind of ultimate dashboard, and I cannot create this kind of stuff. So yeah, why not take a look at empirical software engineering with their tools, with their approaches in the end, with their very specific kind of stuff they were doing here. So I came across another discipline, which is called software analytics in the end. And I found this kind of definition from Tim Mencius and Thomas Zimmerman, which actually fitted what I wanted to do with my ultimate software quality dashboard. Thomas and Tim Mencius, Tom and Tim said that software analytics is, in the end, analytics on software data for managers and software engineers. So that was exactly what I was looking for. So somehow bridging the gap between both worlds with the aim of empowering software development individuals and teams to gain and share insight from their data to make better decisions. So for me, this was kind of an anchor to actually hold on and to see if this kind of stuff actually could work for my daily life as a Java developer. So I took in the next approach. So I started my second attempt in the end. So I took a look from the view of the techniques of software analytics and applied some of the stuff in my daily work. So what is the difference between the first approach for the search for the ultimate dashboard and the second one? Well, it's a more problem-oriented data analysis technique. So if you take a look at some of those problems that are in those legacy systems, we can actually count them. And there are questions that are very frequent. So this one, you can use standard tools, of course. So if you want to know how high your code coverage is within a software system, there's a tool out there because it's a question many people ask. But there's a problem because, how important is it to us how high the test coverage or code coverage in general is for our software system? It may not actually correlate with the amount of questions asked. So it could be that there is a problem that it's of highly interest for our software development team, for our legacy system, but no tool that's available for us can actually answer these kind of questions and fix and get those problems analyzed. So this is where software analytics come into play. In the end, analytics, where you search for your own problem, you want to actually make it visible with some analysis tools, and to bring it on paper, to make it visible, and then to make it solvable and fixable for your team. I've spoken about data very often here, but the thing is, what is the kind of software data a team of developers has? There's plenty of stuff you can actually hold in your hand nowadays. For example, you have some static data like code, or test code, or database schema descriptions like that. You can actually use this kind of stuff to get rid of nasty problems, like if you have authentication problems in a distributed system and you don't know where to look at, you can actually load in all the code from different systems with different technologies and try to find out where the problems are. There's also the category of runtime data. So everything that gets produced during, when you are executing code in the end, like performance reports or log files. These you can also use, for example, if you see that a customer of your application pushes one button on the front end and it triggers 300 database calls, maybe there's something awkward going on there. There's data that you already have produced that you can use to figure out where exactly this problem comes from. I'm sorry. There's also chronological data. So everything that happened in the past, like data in Git repositories, in general, version control systems. So you can find out, for example, if you're facing a completely new software system and the initial creators already left this kind of project, where did they actually spend their work on which part of code parts by mining Git repositories, for example. And last but not least, we have community data. So everything from Stack Overflow, from GitHub issues, from internal developer, chat message systems, and so on. This is also a nice kind of data because you can then look up your favorite library in your legacy system and find out if this is still maintained or if it's abandoned. So this kind of stuff you can do with data that you already have in your hands. But data alone doesn't make software analytics and cannot be applied in practice because everyone can write a bash script and figure out and mangle a little bit with the data that you have. I think the real key is to do this kind of analysis more in a structured way. There, we have, of course, another discipline that can help us with this, which is data science. Data science, I think is the key ingredient because there you get all the not only the tools that you need to mine and, in the end, implement your own analysis, but you get also the methodology, so the approaches, the techniques, the great community that's around there to help you with your data problems. And software data, in the end, is nothing else than analyzing business data if you know how to approach this. And I find it's a really nice fit because, yeah, in this definition of Drew Conway, he says that data science consists of 3 major parts. One is you need to know some math, statistics knowledge. I think every one of us has some, in this. We don't need to know many kind of things here from the math area, but what does it mean, what is the average, for example, is sufficient for this, I guess. And then we have hacking skills, which is another kind of sub-discipline of data science. We are, in the end, developers, so we hack the whole day. We are programming. So we already are covering this kind of area very well. And then we have domain expertise. So for data scientists, it actually means that you have the expertise in the field you are working on, like in chemistry or in engineering. Software developers are also very keen of their own discipline, I hope at least. So for us, domain expertise in software development, who else should have domain expertise in this area? And this is where I then see that data science is a perfect fit somehow for also developers. And I think there's a sweet spot, and we can easily adopt those practices that are part of data science as well. So let's speak about tools as well, because nothing is fun without tools in the end. Methodology doesn't win any prizes. So let's look what tools could be very compatible for using software analytics in our daily practice as developers. I brought some tools with me, so let's start a small show here. And there's nothing fancy here as well, because we're just looking at the discipline of data science, what they are using the whole day long. And there are tools out there like Python as a programming language to analyze problems in a data-driven way. There's also something like pandas, which is a data analysis framework written in Python, which is really fast. You can imagine pandas like a huge Excel worksheet where you actually put in Python code to wrangle around with the data to get an analysis started. And also pandas is a nice entry point or integration point for several data sources, like comma-separated value files that so many tools are exporting. Or you can even read directly from databases that you have if you store your log files in a SQL database or something similar. But I think the main key here is that you, again, don't just write code that analyzes something, but to make it, again, more structurally. And there, I think the third key ingredient is that you try to come up with a method that allows you to make your ideas clear to others. So what are you thinking about when you are analyzing your specific problem? You have to imagine that, in the end, nobody knows and can grasp the problem that you want to address and make more transparent to the others. This is where the notebook approach comes into play. We see here a notebook, more or less, from Albert Einstein. So in the end, some formulas, some visualizations. And these are the ideas, this kind of scientific method from the problem to the solution that we can also use in our digital world. So there's something out there which is called literate statistical programming, where we write down our analysis from the start to the bottom with the context. So what are we trying to figure out in the end? Our ideas, how to make this problem visible. Our analysis, huge pile of code in the end, including a visualization. And the next steps within the conclusion that we can see what actually have we produced and what are the things that we now have to work on with our software development team in the end. You can also check this in the digital world with the tools Jupyter Notebook, which is somehow a piece of software that you also run on your PC. And then you get this nice kind of notebook-like looking programming environment where you can then step by step figure out what's really going on in your software system. I would say with this kind of vehicle, we have some kind of a romantic story here. Code and data are in love with each other because you're constantly changing in between code that is reading in and manipulating the data that you want to use, and with output of data so that you can see what you have produced with your analysis. This is also a nice starter point for you if you're new to the topic, because with this kind of approach, you can share these kind of notebooks with your colleagues. They can take a look at your analysis. They can spot any kind of points of failure or potential misunderstandings of your problem analysis. So make this kind of analysis open to the world in the end. And it has another side benefit here, because if you are in an environment where problems, let's say, are not seen as a favorite topic within your company, you can somehow use this kind of notebook as a proof that such a problem really exists. Because you listed your whole approach, you told the people which kind of data you are actually processing, you tell the people how your analysis, how your shortcuts, how your assumptions work, and what the results are. So this is something, if you need a bulletproof analysis, then notebooks can help you here in this regard. So, just to the slides, let me show you something in action here. I brought some demos with me, how this feels like if you run some tools from data science, if you use it with software data. So what I have here is, for example, the Jupyter Notebook environment I mentioned before. Let's just start this here. It's nothing fancy. You start, as I told you before, a server, and then you get this kind of view. There are already some notebooks in there, but we will also create a new one. So let's do this. We can do this in various languages, like in Python, which is the case here. And then we have this kind of environment. We can start with our analysis. So we can run here Python code. So actually, it's not Python code, but we could. For example, let's make it a string and execute it. And you see the execution, what's happening in the end down below the cell. And this is something, we in the end have code, and then let's call it data that's below this kind of cell. We can even do things that makes more sense. So let's just say a nice string output, of course, for this conference. Nothing fancy here. But we can also add some great things, like, which all of us almost don't like, but we can also switch over to Markdown to add some documentation. So this is not just code and data we will see then, but also steps and descriptions, what we were thinking about in our analysis. And let me just show you a demo that I brought with me, because I want to do something I would call here in a demo software right sizing. What is this all about? So let me just load a quick picture here, or quickly load a picture in there that I can explain it to you. The idea is we have a problem, we have too much code in the end. And we want to get rid of certain parts because we have the idea that something isn't needed anymore. And for this, what could you do if you think about this kind of challenge from a data science perspective? You can search for data that makes it more easier for you to actually prove what kind of parts of a software system are needed and which are not. So you can get this data in various ways. So for example here, we have a Java web application, which runs in a web application server. And in this world, it is possible to actually connect a code coverage mechanism or tool that gathers the information which kind of code was executed and which or not into a nice coverage report. You can also do this with monitoring solutions, for example, but in this case, in this demo, we don't have this because legacy software. And I will show you how can we then go step by step through this kind of data, how we can wrangle it to actually make sense out of this data and to derive next steps. So let's start just by looking at the raw output. What is this code coverage report that we just gathered here? We can also execute, let me just scroll down a little bit here, also bash script if you want to. And I have a data set here with me, which is actually here in the dataset folder. Also code completion is working, that's nice. And it's called jQuery demo. Let's just execute this. And what this is, just displaying here the first 10 entries here, but this is a file for a measurement where a user actually clicked through the application. We recorded this kind of execution. We thought, this is a valid use case across the application and it's okay. And we have here a list of packages, class names, as well as the lines that were missed during this execution of a real user in the end, and the lines that were covered in this use case. So we think, that's a good example to take a look behind the curtains and to see if there are any parts that we can get rid of in the end. So let's take the first step. Let's read the data in. I'm doing this with, of course, pandas. Just importing it here, and then we can read it. We can read in the file as well. Again, there are plenty of possibilities regarding the data source. You can read in CSV files like this one. You can directly read in from clipboard if you want to copy and paste something in your analysis, not recommended. You can read HTML files if they have tables on it. That would be possible if you want to mine your intranet or something like this. Or you can even load in XML if you have something like this. Now, this comes already out of the box. It's nothing fancy. It's what data scientists do for years. So let's just bring this kind of data that we have above here into a so-called data frame. So the same thing as before. We're just loading in the data. And there we have it, without any hassle. Packages, classes, lines missed, and lines covered, which is fine. I'm just storing it into a variable to just be able to use it again, of course. And I'm just listing here the 5 entries of this data set that just read into pandas in the end, so that we have later on a notebook where we can easily scroll through and not have everything in a place where we have to skip several lines. So now we are done in the sense of we are now in a data science world. So from now on, everything is clear regarding the approaches, regarding what we can then apply on this kind of data, how we can transform it, because this is the world where several other millions of people have the expertise in. So, but back to this analysis, what do we want to do? We have to do some data wrangling at first place. That's the ugly part. We have to clean up data before we can start the actual analysis. And luckily, we don't need to clean up data, but we need to summarize it a little bit. Or at least we need here at this place some additional metrics that we can use to do our analysis, because we want to find out which kind of parts of the codes are used and which are not. So in this, we want, for example, add some new data to the existing data frame. For example, it would be nice to have the complete lines of code per class. So let's add them. It's, in the end, an addition like you would do in a normal programming language as well. So just sum up the lines missed with the lines covered. Let's do it this way. And just printing the result down below here. Again, just the 5 first entries so that we don't need to scroll this long. And then we have a new column in the end where we have the sum of lines missed and line covered. Not so spectacular, but we have done it with all the data that were part of this kind of data set. So we can also do this kind of stuff with millions entries absolutely no problem for pandas to do this. It kind of scales in this regard. What we also need is the ratio, so the amount of code that were executed and which were actually missed. So for this, we add another kind of column. We name this a ratio. And it's, in the end, the coverage data divided by the newly added column with the coverage lines column. So we just divide both. And there we see the amount of executed code per class. So from the content and from the wow effect, it's not spectacular again. But easily calculated new data is something that we can easily get into our analysis. So we might have let's say a complicated case. The steps are very similar, and they are easily done and can be easily read here thanks to Python, pandas, and the Jupyter Notebook approach. So there we have very fine-grained data in the end. Maybe 20 classes, 200 classes, 2,000 classes. And there, I think, the actual important part comes into play. We can build abstractions upon this data. So in our case, that means we want to get an overview. So are there any parts in our system that we can get rid of? This was the initial question. And to make a long story short, there was an assumption or a hypothesis that a complete package would not be needed anymore. So we can code this into the data frame as well. So we do and try out some kind of new visualizations here by just grouping data and creating a view that we can easily or more easily reason about. So let's do this with the data that we have. We can take our coverage data here and group it via various columns here. I chose here a package for this. So let's do this. Group everything here from the package, and anything that's in the same package should be also put it or added together. And we will also build the mean out of this kind of data that we put into a package. So for us, this means that we have the ratio column, and we want to calculate the mean of each package to see if there's something awkward going on here, and if there are packages maybe that we can delete in our code base, or are candidates for deleting, would never delete anything based on this analysis directly, but we get a hint that some of these packages we could actually in the future get rid of. So maybe there is something in there. So let's just put this also in a value as well to work with this later on. And last but not least, we also can plot this data directly. So let's do this. Doesn't make any sense from the standard kind of way of plotting things in pandas. So let's do it with the right diagram here. For example, with the bar chart, which is in the horizontal kind of variation. And there you have a nice picture that you can also include in PowerPoint presentations to get money for investigating in more details why this JDBZ package isn't needed anymore. Could be then a valid problem, an opportunity to delete code, or complete nonsense because maybe other companies use this kind of stuff, but it starts more discussions in the future. So this is one approach you can use, standard data science tools, but there's more. So let me switch back to the presentation, because you cannot analyze everything you have in your software system with pandas and Python. Maybe you have software or software data that's highly interconnected, like classes with each other, like modules that have a high amount of coupling in the end. So you need something else. And this is maybe for 10% of the use cases also possible if you take a look at graph data science. So in addition to the normal approaches of data science. There are also tools out there which work also nicely with pandas and Python, called jQAssistant and Neo4j. So jQAssistant is kind of a scanner for structural information. So you can think of it like you have your Java code, and you say, jQAssistant, please scan it. And it scans all the structural information into a graph database called Neo4j. And you get this nicely looking graphs in the end. So here's an example. Code on the right side here. We have a class pet, for example. We have some typical Java bean kind of class here with methods which are declared or is declared from the pet class, or within the pet class we have a field and all the dependencies between those structural or these items in the end. So this is something that you can work on or work with again if you have a problem that falls into this category. And you can even bring it to another view. So for example, on the right side, it's highly interconnected with several items in our source code. But you can say this construct here on the right side is something that we call in our software architecture an entity. So that means that you can then analyze not on the pure low-level details of classes, methods, and so on, but you can analyze your software system based on the various things your software architecture is made of. So, for example, are all entities within a certain package, for example. You can also add other sources of data to it if you want to integrate it, of course. And you can also bring in new information, like you can say, hey, this kind of class belongs to a certain subdomain, a certain module that is important to me. And then bring this up to another level as well. You can then summarize, for example, those metrics that you have just gathered, and reason about it if it's more important to fix the pet, all the stuff in the pet subdomain, or all the stuff regarding specialty. With this kind of view, you don't get just the summarization per module in the end, but in a best case, because you have some domain knowledge within your software system, you bring this up to a level where also managers, for example, can reason about. So that's the thing that you can do here with your very special views for your special software systems in the end, and to try to improve them along the metrics you gathered in the end. You can also query this. Huge amount of code on a slide, but I think we can take a short look how this looks like in reality, because I have another demo here where I scanned as a very small application into the Neo4j database. So let's just look at the picture that we've seen before. So here on the left side, you see some kind of a code inventory, so everything that was scanned from Neo4j and put into Neo4j. We have, for example, here the subdomain kind of high-level view of the software system. We can also then click in this to see which kind of classes belong to this subdomain. And if you double-click, we see all the other data, for example, the changes per classes or per class, per file. So this is a nice data repository that you can then also use for your specific questions, for your problems. You can then query this graph to find out weird stuff. So I brought one example with me. To make a long story short, let's say we want to detect a very weird problem here in our application, which is, I'm sorry, just open it up once more. We want to detect globally written variables. Then we could say, hey, please give me here from this big graph every classes that declare a field that writes a method where the field is actually static, so it's globally available in my source code, and which is not final, so it's not read-only. So this is some potentially bug that could then lead to weird results in your application. We can execute the statement, and down below, we find the spots within our application where this is the case. So for example, here we have in class owner controller a method that writes in line 112 to a static field called owners indexes. So very specific problem just for our context in our software system. And then we can investigate what's behind that. Is this okay, or do we need to fix some stuff here? So just to give you an idea that you can not only visually determine which kind of the software system you need to take a closer look at, but you can also do it with queries in the end. And last but not least, you can also combine both, like the world of Neo4j with pandas. You can query your Neo4j database and get the results back into your pandas data frame. So we can integrate both worlds, the traditional world of data science with the graph data science part, if needed in the end. So these demos you also will find on a slide with a link to it. You can dive deeper into it if you want to get familiar with these kind of analysis techniques later on. So this brings me to the end of my talk. Let's just summarize it. So with this, don't try to find out the one metric to rule them all, to give you the ultimate metric to see where the problems in your software system are or how maintainable it is. That would be my first message. Try to use the two powers of problem-driven first. First have a problem and then try to find a solution. And use data for it. So no gut feeling anymore. And third, don't exaggerate it with your own analysis. So try to actually solve problems. Don't analyze the whole day, because you can, but provide valuable insights within your software system to help others in the end. And with this, thanks a lot. And I'm open for questions now, if you have any. Thank you.
Before the questions, I would like to say that if you are in the ruffle, go to the main stage, because in 5 minutes they will start. If no, and you're interested in the Q&A, then we have one question already. Have you read Adam Thornhill's books, Your Code as a Crime Scene and Software Design, X-Ray, Fixed Technical Debt with Behavior Code Analysis? What do you think?
I haven't read it. I had reviewed it again, so before it was released. So I provided feedback to Adam Thornhill, and I find it a great starting point. I have also both books in my slides as a recommendation if you want to dive deeper into this topic. So great books. I highly recommend those. And
where is AI coming to the picture here?
Maybe AI could fix all the problems, but maybe not, because I think if AI are as good as human programmers, we have still the problems in our legacy systems that we have today. So we maybe need even more kind of data-driven automated analysis, because then we can actually take a look at our AI co-pilots that generated so much code that we cannot easily maintain by hand anymore.
Okay. No more questions online, so the last thing I can do is to give you a small gift from our organizing team. So
thank you very much.
I would like to ask for a round of applause for you, which is really great. And